Hi there, welcome back to my channel. In this video, I'm going to take you through Gauss-Seidel method for linear iterative method. So, in our previous video, we dealt with Jacobi's method. I took you through the process in solving any systems of equation using the Jacobi's iterative method. So, we continue from here on the Gauss-Seidel method. If this is the first time I've been on this channel, kindly subscribe to support and please watch this video to the end. So Gauss-Seidel method is simply a follow-up on the Jacobi method. Okay. The purpose of the iteration, as I said, is for convergence. Convergence. When we say iteration, we've been given an initial guess. Okay. We are trying to guess the final solution. Using our initial guess, you use the initial guess to get subsequent solutions until we approach the exact solution. But as to when and as to the number of iterations to perform to reach that solution depends on what? The convergence. Okay, that's what we call the convergence. There are a lot of factors that affect convergence in the iterative method. The Jacobi is the basic iterative method, but Gauss-Seidel tries to improve the iterative method and speed up the rate of convergence. So let's see how we do it. So we are not going to, we are going straight to expressing this as a system. Okay, so kindly visit the video on the Jacobi so that you can follow up. So for the Gauss-Seidel method, it's very similar to the Jacobi's method. So I always say the first thing to do is express this as an equation. Okay, because the system is AX equals B, so you assume that your x are x1, x2 and x3. Okay, so I simply have 25x1 plus 5x2 plus x3 is equal to 106.8. I'll have 64x1 plus 8x2 plus x3 is equal to 177.2. I'll have 144x1 plus 12x2 plus x3 is equal to 27. So it's equal to 279.2. Okay. So once you express this into the equation form, the next thing to do is you have to check if this system is diagonally dominant. Okay, you have to check if this system is diagonally dominant. And mostly in the exams and for iterative, which is linear iterative method, your systems given are normally what? Diagonally dominant. If not, you have to go by as it is. Okay, you have to surely go by as it is. You don't change it. Okay, so now we are not going to focus on the diagonally dominant parts. So the next thing to do is make x1 the subject here, x2 the subject here, and x3 the subject here. Okay, so for the equation 1, making x1 the subject, what are we getting? X1 is equal to 106.8. We push everything, so we push this and this behind, so we get minus 5x2 minus x3 all over the coefficient of what? X1, 25. My x2 is equal to, so you make x2 the subject in the second equation. Okay, so making x2 the subject in the second equation, I'll have 177.2 minus what? 64x1 minus what? X3 all over what? The coefficient of x2, which is what? 8. Then I move to x3. So making x3 the subject, I'm going to get 279.2 minus 144x1 minus what? 12x2. Okay, so I'll have 12x2 because the coefficient of x3 is 1, it remains the same. Okay, so at this point, what makes this Gauss-Seidel? This is Gauss-Seidel because now let's tackle this. Our initial guess 125. Okay, the difference between Gauss-Seidel and Jacobi is that Gauss-Seidel takes in the current available value. Okay, it takes in the current available value. Take note of this. So if I want to find the value of x1, I need the current value of x2, I need the current value of x3 in order to get the value of x1. in order for me to get x2, I also need the current value of what? I need the current value of x1 and x3. Likewise, whilst in the Jacobi, we use the only the available what? We use the iterant values after each iteration. We use that whole set to find the new values. But for Gauss-Seidel, it's the immediate. So assuming that we had x1 here, this new x1 value will move into the what? Entry of this x1 in the next iteration. Sorry, in the next value within one iteration. So in a single iteration, we can have different values of what? X1, but we use what? The current value of what? X1. But for the Jacobi, for every iteration, you should use the same set of what? Values. So now let's see what we're going to do. So for x1, let's write our first iteration. First iteration. So for x1, I'll have x1 to be equal to 106.8 minus 5. What is my x2? My x2, the guess is 2. Okay, I put 2 there because that is the only available solution we have, is the initial guess. Minus my x3, which is what? 5. All over what? 25. And what am I getting for this? I'm getting 3.6720. What about my x2? My x2 is 177.2 minus 64 multiplying my x1, which is what? 1. Okay, I'll have 1 minus x3, which is what? 5. All over what? X2, I have 8. Okay, and what am I getting? I'm getting my x2 value to be negative 7.8510. So at this point, I move to x3. So my x3 is 279.2 minus 144 multiplying x1, where x1 is what? Do I have a current x1 value? So I'll ask myself, the current x1 value, initial guess is 1025. The initial guess is 10. Sorry, let me write it well. The initial guess is 125. Sorry. So I'll simply write it here. So I have the initial guess. Let me write the initial guess here. So I have 1, 2, and 5. Right. This T is means it means that transpose, okay, is the same as 1, 2, 5. Okay. So it's the same thing. So once we reach here, right? So at this point, you ask yourself, let me see from the x2. So from the x2, that is, I made some mistake here. Let me correct that. So for x2, let me do it well. So in Gauss-Seidel, 177.2 minus 64. So once you get 64, the x1 value here wouldn't be the initial guess 1, but rather will be the new entry of x, which is what? 3.6720, right? Minus our x3, which we don't have any other value except what? 5, right? All over what? 8. And this should rather give us negative 7.8510. Right. So once I get this, I come to my x3. For my x3, I'll have 279.2 minus 144. My x1 will become 3.6720. That's the current value of x1. Okay. Then minus 12x2. What is the x2? My current x2 value is not 2, but rather what? Negative 7.8510. And that will give me my new x3 to be what? My new x3 to be negative 155.36. So let me point this one into the calculator. So I'm having the expression 279.2 minus 144 multiplying 3.6720 minus 5. Sorry, I'm having 279.2 minus 144 multiplying 3.6720 minus 12 multiplying negative 7.8510, right? All over 1. And I'm getting negative 155.36. Yes. So after the first iteration, our x1, x2, x3 is giving us. So I have 3.6720, negative 7.8510. Then the last one is giving us negative 155.36. Okay. So this is the solution here. For the second iteration, I just have to clean here. I don't want to move that way. So my second iteration. So for the second iteration, we simply have to clean our entries and replace them with the current values. That's all. So for my x1, I'll just come back to my formula. I'll have 106.8 minus 5. But here the x2 becomes the current value of x2 here, which is negative 7.8510, minus my x3, which is also the current value, negative 155.36. All this over 25, right? What am I getting? So I'm getting 12.056. So x1 is equal to 12.056. So let me write my second iterant values here, second iteration. So for second iteration, I'll have x1, x2, x3, right? So I'm having the first value to be 12.056 for 12.056, right? So I'll move to the x2. For x2, I'll simply clean this. So for x2, I'll simply have, here's the equation for x2. I have 177.2 minus 64 by x1. What is our x1? We need a current value for x1, and that is exactly what we just solved here. This is the current value. Okay, so I simply write 12.056. Okay, then minus x3. What is my current value for x3? It's rather this. Okay, negative 155.36 all over 8. And what are we getting for that? Our new x2 value. What will our new x2 value be? So our new x2 value is simply giving us negative 54.882. Okay, I simply write it here, negative 54.882. Then I finally come to my x3. So for x3, so I'll simply write and make my substitution for x3. So I'll have x3 to be equal to 279.2 minus 144 multiplying x1. What's the current value for x1? 12.056. You simply write 12.056, right? Then minus, so you have minus 12 multiplying our x2. What is our x2? Our x2 is negative 54. So our x2 is simply negative 54 here, right? Points 882. That's my x2 all over 1. So when I punch this also into the calculator, my new x3 is giving us negative 798. Sorry. So negative 798.34. This is the new value for x3. So I simply write it here, negative 798.34. This is the end of the second iteration. Okay, the end of the second iteration. Yep, the end of the second iteration. So let's see. So at this point, we have our first iteration, we have the second iteration. Okay. So in the problem, it says we should use Gauss-Seidel value to solve, and the number of iteration wasn't stated. Okay. So you can do a number of what iterations. It can be first, it can be second, it can be third, it can be, a number of what iterations. So let's end this video with the second iteration or second iteration value. And one important thing, as we did in the Jacobi, is what we call the absolute relative approximate error. Okay, approximate error. So as we are iterating, our value keeps on converging towards the solution, but there are errors in each stage of iteration. So assuming if you want to find the error between the second and the first iteration, so this is my first iterant value, this is my second iterant value, right? For me to find the error, it's always the current value you have minus the what? The original. That is what you have, the previous. Okay, let me make it previous. Minus the previous all over what? The current times what? 100%. But this one is absolute because it's possible for you to get negative outcome. But once you introduce the absolute, we are interested in the magnitude of what? The error, not the negativity. So here we can get our error, which is normally represented as epsilon a, like this, as, let's say for this one you can have something like 12.056 minus 3.6720, right? All over 12.056 times what? 100%, like that, times 100%. So for this one you can have an error of, let's say I chose the 12.056 as well as my 3.7 values. Okay, 3.7 values. So punching this into the calculator, what are we getting? We are getting 12.056 minus 3.6720 all over 12.056, right, times 100, and this is giving us 69.54%. So this is how we find the absolute error, and this is how we find the iteration in the Gauss-Seidel method. You simply use the current value. Thank you for being with me in this video. Hope seeing you in the subsequent tutorial videos. We'll be solving more problems on this. Don't forget to like, to subscribe, and share.